Hi, welcome back to our discussion of structure and function for pure substances and mixtures at Allen High School. We are having this discussion at the APIBHL level, which would be comparable to your first year college. Now, I'd already filled those in. I want to make a word about ionic compound because it gets us back to continually focusing on this little formula. You can't forget this formula. All of our forces of attraction, even our intermolecular forces, are about their partial charges, but they're still discussing the potential energy, the attractive forces between charges. And I'm hoping to come up with a little activity where you will draw on your table again and use this as your reference point. So let's look at our ionic compounds because I want to show you, we're talking about phase transitions, and I want to link this lattice energy formula with the phase transitions. And in particular, let's zero in on aluminum oxide. Here, I wanted to get two that were just alike. We could do magnesium as well. We could predict where it would lie in between those two. So here are the lattice energy values. So you notice that sodium's charge is +1 and oxide is -2. So the negative charge is the same. Aluminum is +3 and the same -2. So this is for the sodium and this is for the aluminum. Now, the radius of the aluminum ion is going to be less than the radius of the sodium ion. These are an isoelectronic series, and remember we look at the proton to electron ratio there. And if we decrease the radius and increase the charge, we'll see a strong increase in the lattice energy. And you notice it is very strong, like, I don't know what that is, 4 or 5 times greater. All right. Now, if you look at your melting points, that's observed in the fact that aluminum's melting point is nearly double sodium oxides. So as you increase the lattice energy, you increase the melting point. And of course, you would also increase the boiling point. Okay, so that's all this was trying to show, is that structure function link for ionics using this lattice energy formula here. I can't emphasize enough how important that is. All right, now I'm not going to spend a whole lot of time on this chart, but I do want to point out a few things. I spent a lot of time trying to design a summary chart for you. This will definitely help you when we do our inquiries in class, the activities that I've designed in class. And there is a wealth of information on this. If you linked this to the pictures that I had above where I talked about what we were breaking when I was showing the bonds and the IMFs that we're breaking, if I could link those together, I can't because it's already a lot of, it's already a page here. But if you could overlay those somehow on this, it's a very powerful summary of everything we're going to talk about in this whole unit. And tons of multiple choice questions are addressed in this chart. I could probably sit here and write 25 multiple choice questions in a heartbeat for these. So here's what I've done. Hopefully you've got a colored printer at home. Otherwise, the black and white will work. It's just not quite as visual. I've got our network covalent. These are our what the types of examples of types of elements. So network covalent, the definition of it, the definition of metallic, the definition of ionic, the definition of your molecular. So this is what we're talking more about, your molecular, those discrete molecules. Okay? Now, in the green, I've discussed the types of models that we've been using to try to understand them. And again, you need to be able to draw models. So you should be able to draw a model of the sea of electron. You should be able to draw a model of ionics with alternating positive and negative charges. In our textbook, it'll talk about crystal structures, but we're not going to discuss crystal structures. Okay? So those are the types of models. We used VSEPR and hybridization. You can use VSEPR and hybridization with network covalent as well. All right. Now, molecular is broken down into two types, polar covalent and non-polar covalent. Okay. Now, what I'm trying to show here is in words what I was showing in that picture. What are you breaking? What are the attractive forces being broken? Okay, and we could talk about being formed as well, but remember, it takes to break. Takes to break. All right, here we're breaking, remember, covalent bonds. Here we're breaking that kind of negative positive electrostatic. Some people do call this a type of covalent, if that helps. Just be cautious using that word because it's really called a metallic bond. But it's an electrostatic attraction between metal ions and those freed, delocalized valence electrons. Instead, you know what? I know other books talk about that. I'm just not comfortable using that word covalent there, so I'm going to quit doing that. All right. Ionic electrostatic attractions. All right, here it's an electrostatic attraction as well, but it's an electrostatic between partial, and I know this is hard to see on the screen, but you've got it in front of you. So those of you who don't, you can go to my website at Allen ISD, and I have notes that follow these videos. Okay, allenisd.org, go to the high school and hunt me down. All right, now, this is a description of what happens during a phase change, what you're breaking. Once you've narrowed it down to covalent, ask yourself if it is polar or nonpolar. If it's nonpolar, the only thing available are London dispersion forces. Okay. If it's polar, in addition to those underlying London dispersion, and that's what this little phrase talks about, we have hydrogen bonding if it's an H to an FON. So you can say chemistry is fun, H to an F, H to an O, H to an N. I don't know how you want to memorize it. Okay, dipole is all other polar covalent molecules. So I always ask myself, okay, is it polar covalent or non-polar covalent? Once I've decided it's polar covalent, I say, well, can it hydrogen bond? If the answer to that is no, then by default it's a more simple dipole. Okay, now, this gives you, I think, some good examples as well. I would focus especially on some of these. You need to memorize those like classic examples of network covalent because I see them all the time. And we're going to talk a little bit more about alloys in the chapter 7 section of this. Okay, so I would keep this handy because it's going to help you even from day one. I will try to remind you to pull this out for day one as well. And then we're going to move on to intermolecular forces and some of the other properties in addition to boiling and melting and phase transitions. So until then, this is signing off.